is recent progress in sub-quantum limited interferometry. Now, this is for applications to gravitational wave interferometers, but there are other applications, obviously. And anytime you see sub-quantum noise limit in this talk, think squeezing, because I'm not really going to talk about the other ways to go sub. Okay, so I want to point out, most importantly, the people whose work I'm going to show today. There's a group at MIT, and these people I can list because I kind of know them somewhat well. We have close collaborators at Caltech, at the Australian National University, and at the University of Hanover. Now, there's actually something very special about giving a squeezing talk at Caltech. And really, it's because it all started here in some ways in the late 70s and early 80s in terms of both Q&D techniques and squeezing in particular with the work of Carl Caves and Kip's group and Bill Unruh. And I actually have dug out from the museum proof that it all started at Caltech. This is the original squeezing Q&D t-shirt from my dearest collaborator at Caltech, Stan Whitcomb. And he also told me, well, it doesn't really fit me anymore, you can actually have it. So now I can really take my jacket off, it's much too warm for it. So this, I'm told this was made by Caves. Is this, yeah, so in like the very early 80s. So it really did all begin here. And what I want to talk to you about today is that these ideas that at the time were so esoteric and so much in the realm of theory have now really become experiments, and I would like you to carry away the message that these experiments are getting closer and closer to what I would call the real deal, which is we want to try to use squeezing in a gravitational wave interferometer or get one out of it. Both techniques I'll talk about. Now that I've said all these nice things about Caltech, sorry about the Canon. So the outline of my talk is I'm going to introduce a little bit the quantum noise limits in interferometers and how they come about. And so that we start thinking about this problem quantum mechanically, I also will give you a small little introduction to quantum optics, just the basic tools that we're going to need for this talk. Then I'll talk a little bit about sub-quantum noise, and in all of these cases, like I said, I'm going to talk about squeeze states. And when we talk about squeeze states, you'll see shortly we always talk about squeezing a vacuum state, okay? So what we'll do then is set some requirements, which sets up our wish list. What are the things we'd love to have out of a squeezer? And I'm going to show you two ways in which we actually make these squeeze states and the experimental status of each of these. And I'll talk about two kinds of squeeze state generation. One is done with using nonlinear optics, and we call that crystal squeezing. And there's another way, which is using radiation pressure effects, and we call that ponderomotive squeezing. It's another word that was coined in these hereabouts. And then finally, if I have some time, I want to talk a tiny bit about how this kind of squeezing actually leads us to the world of macroscopic quantum measurement, which is something new and interesting that's also been going on theoretically in Kip's group here. So our quantum tail actually begins with the first of our quantum interferometers, and that's initial LIGO. Now, in initial LIGO, we have an input laser power of 6 watts, and that gives us some circulating power in the arm cavities of around 20 kilowatts, and we have 10 kilogram mirrors. So what we've always known about is the shot noise, which is part of the limiting noise at above about 150 hertz in initial LIGO. The part we never really talk about, which is another piece of the quantum noise limit, is radiation pressure noise, and that is really in initial LIGO masked by the seismic noise. So we've never really had to deal with the other side of the quantum noise, which comes from intensity fluctuations. So the picture we carry away then is when we think of quantum of measuring, making a position measurement, we have the shot noise, and that's always given in our case by the uncertainty in the number of photons. So our signal to noise ratio would go as 1 over the power on the beam splitter. So you turn up the power on the beam splitter, and you can make a more precise measurement of the displacement of your mirror. Now, the competing effect is the momentum that's imparted by the photons. So you turn up the power, and they start imparting the fluctuations in the number of photons, starts giving bigger kicks to the mirror. And that actually limits how well you can measure the mirror position. And so now what you have is this power turns up in the numerator. And it's also scaled, by the way, because you're now applying forces to this movable mirror. It scales with the mass of the mirror and the frequency at which you measure. And in this case, you turn up the power, and your effect gets worse. And that's what gives us this optimum input power dependence in initial LIGO. Now, in advanced LIGO, the story changes a little bit. Our input laser power is going to be well in the excess of 100 watts. And that gives rise to something like half a megawatt of power circulating in the arm cavities. And even though the mirrors get more massive, what you notice is the prediction is pretty clearly that in this region here, you'll still have shot noise. And it's better than initial LIGO, because indeed we turn the laser power up. But in this region here now, what you have is, because the seismic noise is improved, in this region you're limited by the radiation pressure noise. So this is how our story began. What should we do about that? And so I'm not going back to the very early days of squeezing, but really just where we're at in this millennium. So a little primer on quantum optics, and I'll talk about these things a little bit, so I might as well bring you in. In the classical optics picture, you always think about the amplitude and phase of your electric field, and you can write the power as the field squared. So these are the kinds of things we measure, is the intensity on a photodetector given by this quantity here. And in phasor representation, the length of your phasor is the amplitude, and the angle gives you phase. Now, in the quantum world, we have annihilation and creation operators, which are these quantities here. And then the number of photons, the photons in a given state, is given by this product operator. Now, A and A dagger are not observables. They're non-Hermitian, but you can always create a Hermitian pair out of them. And this is the only reason to put this up here is we talk repeatedly in terms of quadratures and quadrature operators, and that's our literature is full of that. So I just want to point out to you that they're not very esoteric objects. What these are they're constructed from these non-Hermitian operators, but these two quadrature operators are observable, and they're associated with the amplitude and with the phase. And that's really the main message to carry away from this slide. And the final thing is, you can also then represent the fluctuations in amplitude and phase via these quantities that are also associated with operators. Okay, so that's our starting point. Now, the Heisenberg, so if you say, okay, what's the next difference between classical and quantum optics? We have, as with all quantum systems, the Heisenberg uncertainty principle. And the main thing that requires for us is, in fact, that just as we have position and momentum uncertainty for a particle, we have these conjugate observables, our amplitude and phase quadrature, and those have to also obey a Heisenberg uncertainty principle. Okay, so that sort of sets up the stage for the minimum uncertainty that you can have in an optical field. Now, lots of a couple of equations here, nothing particularly important for you to carry away from here, except that correlations are really one of the key ingredients to making subquantum states. So the idea is that you can always have some total noise that's given by the noise sources, the shot noise and the radiation pressure noise. And if you can correlate them, then you get an extra term whose sign you get to control. And that's really the way that we can think of the noise being increased or decreased. Now, in the case of the quantum uncertainty principle, what that says is that when your correlated part is non-zero, you can actually do better than the quantum limit. Okay? So I would say probably the rest of the talk almost is going to be associated with how do you correlate these quadratures. This is probably the way to think about everything we do in the squeezing world. And the obvious answer is you want to make the noise in each quadrature independent of that in the other. And the two processes, and the processes we normally think of are nonlinear coupling processes. And I'll explain that in a moment. And that gives rise to squeeze states of light at vacuum. So what is a squeeze state? A squeeze state, now imagine we go back to our classical picture. You think of a phasor. Here's your real and imaginary part of your E field. The length of the vector is the magnitude, and the angle of this vector is the phase of your electromagnetic field. And in the case of the quantum equivalent of that, you replace your amplitude and phase with your two quadrature operators. And now, because of the uncertainty principle, the tip of your vector has an uncertainty on it. You cannot determine its position in this phase space better than the fuzzball. And that fuzzball is given by that minimum certainty if this is a coherent state. Okay? The vacuum state really is one of the things that often troubles people. What does it mean to have a vacuum state? The vacuum state is essentially the same as a coherent state in terms of its uncertainty, except it has no coherent amplitude. So in a thought experiment, you could set up a measurement to measure a coherent state and then just keep dialing its intensity down till you walk yourself down to this point here in phase space, and you'd still be left with the noise on the vacuum state. Amplitude squeezing then would look like this. Here is the direction of the amplitude, and in this direction you have some squeezing. Now notice the price that you pay is that in the orthogonal direction you get increased noise, and that's necessary to make sure Heisenberg uncertainty principle is not violated. It's preserved. And finally, you can have phase squeezing, which is that along the phase angle direction you have some squeeze state. Okay, so how does this work in an interferometer? So let's take a simple case, and we'll take a simple case being a Michelson interferometer. And this is actually the way that Caves taught us to think about noise in a differential measurement like this. So imagine you have your laser and it goes along the two arms, and because this is, you detect here at a dark port, all of the laser light, and in fact all of the fluctuations on the laser light should go back towards the laser. So the measurement you make here still has this shot noise. Now how can we explain that if we said that all the noise went back towards the laser? And Cave's explanation was the following. In fact, what you have over here is you have an unused port of this beam splitter, and into that unused port sneaks in some vacuum state. Now keep in mind our two quadratures, here's your vacuum state. So vacuum likes to go in anywhere where there's an open port to the system. This is going to be another important thing to notice. So when you actually make the measurement, if you think of this yellow arrow as being your signal vector, then what you have is its tip is uncertain because the vacuum state has to beat with that at this output here. Imagine now that you injected into your interferometer a squeeze state and squeezed along this direction. Now when you make the same measurement, your signal vector has a smaller noise associated with it along the measurement axis. And that's the picture of why injecting a squeezed vacuum state into the interferometer will give you an improved measurement sensitivity. Now notice if your signal had been along the amplitude direction, you would have been hosed. So it does turn out that that's not always the case. In fact, in most interferometer configurations, you do actually have these signals being in both quadratures depending on the frequency and so on. So creating the squeeze state and injecting it then also needs a little bit more cleverness to make frequency-dependent squeezing so you can take advantage of that. Eric?
Can I ask a stupid question here? I'm imagining the vacuum has essentially zero amplitude, but it has to have some sort of a k-vector in the direction in which it propagates. And you've talked about the part of the vacuum that goes into the interferometer and then circles around and comes back out. So what about the equal amount that's coming towards the
So the thing you have to keep in mind is that the only part of the vacuum, I mean the vacuum populates all modes. The only part of the vacuum that you care about is the one that overlaps with your signal mode. And so it's that overlap. So you're picking out all possible vacuum modes that propagate, and you only have the beat note with the mode of your measurement.
So the stuff that started coming out of the dark port in the first place, it didn't necessarily originate in the interferometer.
Right. Yeah. It has no. I mean, you only make the overlap with the mode that overlaps with your measurement mode. So that's the one way that one can inject squeezing into an interferometer and get a better measurement. Now it turns out that you can also produce squeezing inside an interferometer. And the way to think about that is, imagine you have some input state here, and this input state may well be a vacuum state, just as we talked about. And what you find then is that the output of the interferometer looks like this. So B1 and B2 are associated with those two quadratures. You can think of them as the amplitude and phase quadratures. And in fact, the amplitude of the input vacuum travels into the interferometer and comes back unchanged as amplitude of the output. But the phase of the interferometer contains an extra term in it from the amplitude that's given by this coupling coefficient here. So you start with some amplitude that goes back out here, and in the phase quadrature, you actually measure some of that amplitude in addition to just the phase noise coming in here. And then you have some signal. Now, what causes that to happen? You can think of a very schematic picture here. Here you start with your input vacuum state. And it enters the anisymmetric port, and it travels along. And right about there, the fluctuations over here beat against the light inside this cavity and cause your mirror to move. Now, so what you have in this situation is that the mirror position is changed by the amplitude fluctuations of the light, and those are then imposed onto the phase of the light by the mirror motion. And what you end up with then is you get this coupling between the amplitude and phase, and you get a squeeze state that, as it propagates outwards, also is rotating. And it comes out at your output port here, in this output B. It's squeezed, and it has some squeeze angle associated with it. So that's the picture for how an interferometer might produce squeezing. And that's due to the fact that the mirrors are movable and respond to the radiation pressure force. So that's another key point. Okay, so those are sort of the key ingredients of this system that we wanted to sort of just set the stage with. So the next thing I want to talk about is where are we at with subquantum interferometers. So what we had seen earlier was this particular curve of an advanced LIGO interferometer in strain versus frequency. And what I have plotted over here are the red curve is essentially another version of the blue curve, just with a different signal detuning. So it's a broadband case instead of a narrow band case. And you can see that what you get in the case of the broadband case is you gain sensitivity in the edges, but you lose sensitivity in this region here, comparing the red to the blue. Now, what I have also plotted on this is the green curve, and what it is I've taken the broadband case and I've injected squeezing into this interferometer. So what we do then with this, you noticed a couple of things right away. I see improvement in this region, and this is the region where I'm limited by shot noise. So I've injected squeezing that improves my sensitivity at frequencies where the shot noise dominates. But notice now what happened at low frequencies. At low frequencies, I've actually ruined my sensitivity a little bit in this region here, and that's because my squeeze state was aligned with the signal vector at these frequencies, but at those frequencies, the signal vector is actually probing something along the long section of my ellipse. So this is basically the case that what we really would need if you wanted to ideally squeeze at all frequencies, you need a squeeze state that is frequency dependent, that looks like amplitude squeezing at low frequencies and looks like phase squeezing at high frequencies. That's the picture to take away from here. So is squeezing really the fix? And obviously, if I'm going to talk to you for a whole hour about it, I think so. But the things that you want to keep in mind are that if you really want to do better than the shot noise limit, you have two choices, basically. You can get more power into the interferometer, and there are several people in the room working on more power, and it's a hard problem. Not that squeezing is easier, but or you can squeeze. And so you can either take one hard problem or another to make this improvement. And the other thing to keep in mind is that if you have a particular power, if you want to reach a particular sensitivity and you can't handle that much power in your interferometer, then you really could reduce the shot noise by squeezing. So you can think of the squeezing also as a knob you could use to decide how much power you really want to put into your interferometer. So here are then the requirements. This is what we would like. We'd like squeezing at low frequencies. And keep in mind that the plots that I showed you are all in our frequency band of detection, sort of 10 hertz to 10 kilohertz. We would like to have this frequency-dependent squeezing. We would like to have lots of squeezing. This is, of course, the more is better philosophy. And we'd like to have it be a long-term, stably operating squeeze source. And this list of requirements, I should say, was initially compiled in 2002 when we first started looking at the problem and saying, there was a community out there that does squeezing, and we asked, why don't we just take their squeezer and stick it on our interferometer? And these were the problems that we had. The squeezing occurred at megahertzes. There were no long-term locked squeeze states available. The level of squeezing was around, could get 5 or 6 dB, so you could get something that's equivalent of a noise reduction of 80-ish%. And of course, nobody really had given any thought to making frequency-dependent squeezing. The methods that we then looked at, we looked at this nonlinear optical systems, and I'll talk about that a little bit more in detail. These use the Chi2 or Chi3 nonlinear susceptibilities of optical materials to make that correlation or coupling in a system. Or we could also try to use radiation pressure effects in interferometers, keeping in mind that squeezing is also produced inside the interferometer. Wouldn't it be nice if we could extract it? And we embarked on this in this direction here with looking at this precisely because I went to see Kip one afternoon and he said, get some squeezing out of the interferometer. I don't know if crystals will work. And this is how we started on this road. So no thank you, Kip. So let me now break my talk up into 2 parts. So I'll talk a little bit about the crystal squeezing and experimental results from that. Where are we at and as a community? And keep in mind the work I'm going to show include our own labs and our collaborators at the ANU and at Hanover. And then I'll end with talking about radiation pressure-induced squeezing, which is extremely rich, and I don't know how far I'll get with that. So the basic principle of using a nonlinear crystal for squeezing comes about in the following way. These are toy pictures. As you know, photons aren't really balls, but what you can think of is that you have a device, and you'll soon learn what these devices are called. They're usually called parametric oscillators or amplifiers or SHGs. And the Hamiltonian, or the energy of that device, is given by terms that look like this. Now, these might look a little frightening, but they're actually easy to follow. The kappa in here is a nonlinear coupling term. It's a property of the material. And the first term here basically says this is a creation operator. So this corresponds to creating 2 photons in mode A and destroying one in mode B. Now, what is mode A and mode B? You can think of them literally as 2 colors of photons. So mode A could be a low energy red photon, and mode B could be a photon of twice that energy, a green photon. So an infrared and a green photon, for example. On this side of the Hamiltonian, you have exactly the opposite going on, which is that you destroy 2 A-mode photons to create 1 B-mode photon. And this is called second harmonic generation. You take your nonlinear medium and you inject it with 2 A-mode photons, so 2 infrared photons, and out of that comes 1 green photon. So you've made, and by the way, many green lasers that you use now, green solid-state lasers, are all based on this principle of second harmonic generation, as are most RGB lasers. Then on the other side, what you see is a process of amplification is easy to see. You start off with a system where you inject 1 B photon, so 1 green and 1 red, and by energy conservation, what you get out is a red photon and 2 red photons here whose properties are correlated. Okay, so that's the other thing that you have to keep in mind, that the properties of these, of these photons that come out are correlated because they're produced by a single process inside this nonlinear medium. So from here on, our system, these are little black boxes, but that's essentially the process that's going on in there. Now, a schematic of how this would look in a lab. So there is, in fact, our little black box. It's actually not black at all. It's a pristine, clear crystal, if the photo was better. What you do here is you start off with some laser light, in our case at 1064 nanometers, or 1 micron. And the first thing you do is you use SHG to produce a lot of green light. So you produce some 532 nanometer photons. And that's the SHG process. And now what you do is you then take another nonlinear crystal here, and you feed it with green photons from here, red photons from here, and inside here the nonlinear coupling gives you your squeezed photons. Now, if you wanted to make squeezed vacuum instead of squeezed light, what might you do? What you would do is, the thing that gets squeezed is this beam that's coming here. So you basically just start attenuating it. And as you attenuate it, your vacuum mode leaks in here, and you get a squeezed vacuum mode coming out. So in a practical sense, when you want to make a squeezed vacuum, you put a beam block here. Now, this is filled with terrible problems because, of course, once you have no coherent amplitude here, it's hard to know how to lock this cavity and so on. These are details that I'll spare you. But as you'll see from some of the experimental results I'll show you coming up, these are increasingly solved problems. Okay. Oh, there's one other little caveat that I should say. There's this little PZT mirror here, and that plays an important role in this system, because depending on the phase relationship between the green beam and the red beam, you get either squeezing or anti-squeezing. Remember, that's how you rotate that ellipse. And so, what we do is we control which quadrature we measure at our measurement port, which I haven't shown in detail with the phase of the green beam. Okay, here is a schematic of a system like that, but I'll spare you the details. It looks a little busy. A more intricate one would look even busier. But if you really want to have a look at a system like this in operation, go to the 40 meter. Now, what we see then, here is some data from one of our early squeezers. Now here, as a function of time, the green curve here is what we would call shot noise. So we start off by measuring the shot noise in our detection system. And then as we scan that phase of the pump and seed, remember that PZT, you would see here is squeezing, you go below the shot noise, and here is anti-squeezing, and so on. Okay, so this is essentially shows you two things that are very interesting in this curve here. The one is that you see about 2 dB of squeezing in this curve, and you see quite a large amount, 6 dB of what's called anti-squeezing. So what that tells you right away is this is not a very pure state. What it also tells you is that intrinsic in your squeezer, you can produce as much as 6 dB of squeezing, because the squeezer inherently will produce a pure state. So where is the rest of this 6 dB? And the rest of the 6 dB is affected by losses in your system. So that's when people, now this is another thing that happens a lot in the literature, people talk about intrinsic squeezing versus detected squeezing. And this is what you can detect once you take a real experiment and all of its losses into account. But this is the level of the intrinsic squeezing that can be produced in a squeezer like this. Now, that was squeezing where I showed you what happens when you scan that squeeze angle. This is data now from the ANU group. This is by Kirk McKenzie et al. In 2004, and this was actually a very important piece of data in the community. And the reason why is that people had been working on squeezing at several megahertzes. And the real reason is when you think about squeezing, you think, okay, I start with shot noise, and then I go below shot noise. And in most laboratory apparatuses, lasers and detection systems aren't really shot noise limited till a couple of megahertz. So this was the stumbling block here. So you start off with something that's not shot noise limited till a couple of megahertz. Now, in the case of the ANU experiment, there's a crucial thing that you can see. Again, what you notice is that the red curve is the shot noise. So often these measurements are all given relative to the quantum limit or the shot noise limit. So that's the 0 dB point here. And the purple curve, the black curve then is what we would say was the low frequency squeezing. You can see we're now in sort of the few hundred hertz region. This is 300 hertz here. So this was a really important measurement to do. And the key feature that was important about it is that what we realized is that the thing that you can ask, what's the purple curve? You see all these crazy features in there. So the purple curve is essentially the same as the black curve, except that there were stray photons at 1 micron inside our OPO. And those few photons that get in there, that are in that mode, the noise from those corrupts the measurement. So the key feature to this was, if you want to squeeze vacuum, you better have good vacuum. And that was the main lesson to learn from this. But once this was discovered now routinely in our labs at MIT and also at Hanover, people are squeezing in the audio band, because the name of the game is to isolate your OPO from all the stray light.
So is that the key thing that enabled you to get down into the audio band?
Yeah, and in fact, they have a series of measurements that I don't show here where they show, it's actually very neat, they show the attenuation of the seed, and to the point where there was so little that you could really get to this point. And the Hanover group has shown even lower frequencies. This is, I'll talk about that next time I'm here, because it's very new still. So so I would say this is probably one of the, so I'm going to talk about a few big breakthroughs that make this look like a very feasible thing to do, and I would say this is one of them. Now, you can also ask, have people ever really done anything useful with the squeezing, really injected squeezing into an interferometer and seen some improvement in the shot noise limited performance of the interferometer? And the answer is yes, absolutely. And the first one was actually done in the late 80s in Jeff Kimball's group. Here I show some, and that was in a simple Michelson interferometer of the kind, the toy model I showed you earlier. Here I show something a little bit more recent. The cutoff part here is a 2002 measurement, again done by Kirk McKenzie at the ANU. Now, keep in mind, the next set of measurements I show are all megahertz measurements. So we haven't really done sub megahertz inside of interferometers, with the exception of the new Hanover result, which I won't talk about. So what we see in here is you start off with your laser and you have your, in this case, your pink box that makes your squeeze state. Now here is a power recycled Michelson interferometer. There's the power recycling mirror, beam splitter, and 2 end mirrors. And you inject your squeezing into this interferometer using a Faraday isolator. It's just a way of making some light go this way and not that way, without making, and still preserving its polarization. And what happens then is you make your measurement over here in the usual way of your so-called gravitational wave output. And the measurement they make is they wiggle these mirrors differentially, and they make a measurement here, and they ask, how much better can I do with my squeeze source? And here is the data. So the very first thing you see are these two curves here. This is the curve if you have only your simple Michelson. Now this bump comes from the fact that that's the frequency at which they generate their gravitational wave signal. Okay, and you notice that there's your signal, and there along here is your noise. The next thing they do is they turn on the power recycling, and so indeed your power recycling improves your signal to noise because of the power recycling gain. And then the interesting thing to compare to really is the red curve and the cyan curve. So here is your signal to noise for the non-squeeze case. Then they inject about 2 dB of squeezing, and notice that the signal remains the same and the noise comes down. And so that's the standard way in which people show signal to noise improvement inside an interferometer. Now, Another measurement, more recent, from 2005, is done in the Hanover group. And there, what you see is actually something that's even, is also very interesting. The title, I'm sorry, here remains wrong. This is actually now done in a signal recycled interferometer as opposed to a power recycled interferometer. And the thing that's very nice to see here is, here again, the black curve is your shot noise. And these two curves are what you would get if you had frequency-dependent independent squeezing going in. So you see some improvement at these frequencies and these, but here you make it worse. And then they actually applied a filter cavity. And I'm going to say very little about filter cavities other than that they're a way of making frequency-dependent squeezing. And then they see this sort of broadband improvement in squeezing. So this is a nice demonstration because it also shows the ability to produce frequency-dependent squeezing and inject it into an interferometer and see the improvement. Okay, so with crystal squeezing, our story is we have squeezing at audio frequencies. In the last 5 years here, I would say in the last 4 years, here are the things that have happened. We have improved crystals, and this is the idea here is to try and bring those losses down so we can really extract more of the squeezing that's intrinsically produced. We don't have any big improvements to report from those yet. We filter cavities for frequency-dependent squeezing. And these are, I should say, these are really in terms of experimental proofs of things. We have detailed calculations of the noise couplings, and what we establish is that there really are not fundamental limits in these nonlinear optical systems that should stop us if we can control the losses and learn about controlling them, controlling the cavity resonances and so on. These have been tried on tabletop configurations. All the data I showed you are from that. Coherently controlled squeezing is more or less a solved problem at this point, although I won't say much about it. Now, we had wanted 10 dB of squeezing, and we still do. And where are we with that? We're at about 3 or 4 at most. Actually, I would say 4 is already a stretch. We're at about 3 dB in the 100 hertz region. So this is an open area where we still have improvements to make. And we wanted to put squeezing inside a gravitational wave interferometer. And we have, in fact, tabletop interferometers, and we're bringing it to the 40 meters soon. And I won't say when we'll go with long baseline interferometers with this. But the message I'd like you to carry away is that crystal-based squeezing is now sort of mature enough that we really can start thinking about what's the next step to really putting it on a long baseline interferometer. So.
Are there filter cavities for the audio frequencies?
So that's actually a very, very good question, Jay. And the answer is no, none that have been demonstrated. And the reason is that at audio frequencies, that means, the frequency at which the filter cavity filters is given by its line width, its pole frequency. So if you want something that has effects at 100 hertz, you either make it very long, kilometer scales, or you make it very low loss, or as you go through your reading list tonight, you can also try other ideas which are out there, like using standard atomic physics techniques like electromagnetically induced transparency. But those are speculative. These are not experimentally demonstrated. But no, so at low frequencies, the filter cavity is not there. So anyway.
For LIGO, you do have a possibility of 4 kilometer cavity.
Yes, you do. It's it's rife with problems that would have to also be solved, but you have an option for them. So I agree with that. So
the one problem that people have argued about, at least to me, is that light scattering. I don't think that's a serious issue.
I kind of agree. I think we already know from Hanford we run 2 cavities with and these would, by the way, be actually, interestingly enough, when you use a filter cavity, you actually are, there's not a lot of light in there. You have to get some light in there to lock the cavity, but this is really a vacuum that you're filtering. So, but I think that's a detail that really still has to be worked out. So this is the reading list for tonight. That gives you a background to all the things I've talked about on crystal squeezing. And now I switch gears. Does anyone need a break? Okay, so now I'd like to talk about radiation pressure induced squeezing. And the principle is actually, there are some nice parallels. So the principle is the one I already showed you in my cartoon. You take your cavity with high stored power and a phase-sensitive readout. Intensity fluctuations via the radiation pressure drive the position of the mirror, and the mirror then puts that onto the phase of the light. Now the analogy with nonlinear optical media comes along in the way of saying, I mean, the way that these non-optical media work is you have an index of refraction that's intensity dependent. That's really what that nonlinear coupling is. And in this case, what you're doing is you also have a phase shift of the light that's intensity dependent. And that's really the analogy that you can carry away. But beyond that, no more. So the experimental concept. So let me just give you some context here. I'm going to talk about an experiment. It's an experiment that's ongoing, and I'm going to tell you how we do it, where we're at with it. So the idea is that we want to use a tabletop interferometer to extract the squeeze light, squeeze state from. We want to use the radiation pressure as a squeezing mechanism. And there are a couple of things that are very important and interesting. So what this relies on is that it relies on the quantum mechanics of this optical field and mechanical oscillator coupling, and I'll say a little bit more about that towards the end. And another thing to carry away is that the squeezing is produced even when you're far worse than the SQL. People really get confused on that. How can you squeeze if you're not at the standard quantum limit? And I'll show you how that comes about. It comes about due to a little device we use called an optical spring, and it's going to feature very importantly in the rest of my talk because it's really the key ingredient actually to this experiment. So here is a schematic of the experiment, and it looks to very many people like any old gravitational wave interferometer would look. We have a wad of laser light that's split between a beam splitter and goes into two arm cavities. And these are fairly high finesse arm cavities. We store about 10 kilowatts of power in each one. Now the key difference is that these two mirrors are 1/4 kilogram. They're sort of 3 inches big. So they're identical to LIGO mode cleaner mirrors. But the two end mirrors are small 1 gram, 12 millimeter diameter mirrors. And the reason is that we need them to be able to respond to the radiation pressure force. So the key ingredients then are that you have to have these low mass mechanical oscillators, and they have to also be low noise. Keep in mind, thermal noise is an issue, so we have to make them be low thermal noise objects. In our case, they're 1 gram and with a 1 hertz resonant frequency. We need high circulating power, 10 kilowatts, and that leads to a finesse of, that amounts to finesse of about 15,000. That's not hard. We're making that now. And another key ingredient is a differential measurement. You could ask, why don't you just do this with one cavity? And the problem with the one cavity is that the laser noise completely dominates the measurement. So you have to have a differential measurement with a reasonably good common mode rejection ratio at the beam splitter so that you can see the squeezing here and make sure all your laser noise goes back that way. And finally, there's the optical spring, and the optical spring has two very important features. One is something we call noise suppression. I'll talk about that, but the basic principle to carry away is that when you couple these mirror oscillators to an optical spring as opposed to a mechanical one, you actually get all of the rigidity from this spring without the thermal noise hit. That's the message to carry away. The other piece of it that's very important is that because you make a very rigid optical spring, at frequencies below the optomechanical resonance, your response to forces is flat. So you actually can get frequency independent squeezing. Otherwise, your squeezing would be falling off as 1 over f squared from the mirror. And I'll explain that much better in a minute when I show you what I really mean. So let's talk about the optical spring. I already told you this. So the thing that happens is this might be the most illuminative picture to see. And essentially what I have here is a force per displacement. It's a function of frequency. So they are everyday, ordinary, simple harmonic oscillator. And in the case, the red line refers either to a free mass, or if I put a little resonance there, would be my 1 hertz oscillator. And now what happens when you couple this to a much more rigid spring? And what happens is, of course, is that you move the resonant frequency out to some higher frequency, and in this region here you have the flat response. Now, why couldn't I just do this with a mechanical spring? Why can't I just tie my mirror to a nice old clunk spring? And the answer is the thermal noise from the mechanical spring would dominate the whole motion. So the key feature then is to couple it to a spring that doesn't change the thermal noise, but gives us this optomechanical rigidity. So changes the whole response to external forces for the mirror. And so I already talked about the thermal noise here. So we like to think of it as a nearly noiseless spring, and I'll say a bit more about the noiselessness. It turns out there are very rich dynamical issues in there.
Hey, Nergis?
Yeah?
Does that statement that the mechanical springs wash out the squeezing, does that apply for even very high Q things? Is that frequency independent?
Yeah, so we've certainly made numbers with just how high could you go. So keep in mind what we're talking about is we're taking a 1 hertz. I mean, you can keep in mind because I haven't told you this yet, but I was about to tell you in a couple of minutes that the optical spring that we use takes a 1 hertz oscillator and moves it out to 5 kilohertz. So now you can make the number for what that corresponds to in Q, which goes as frequency squared. And you'll see that it's a Q that mechanically is not feasible. And we already assume a 10 to the minus 5 Q for our mechanical oscillator. So you'll see that in the numbers that it wouldn't work out. You could, but it wouldn't work out. Okay, so how do you make an optical spring? You take an optical cavity, like this one, 2 mirrors facing each other, and you detune it. So here is the cavity on perfect resonance, center of the curve. This is power on this axis versus detuning from resonance. And if you detune it to this side of the resonance, what you find is that you have a restoring force. And how does that work? What happens is, imagine that the length of the cavity increases. So you make a little increase in the length of the cavity. Your mirror moves out. Now what happens is, as it moves out, it feels a lowering of the power. It actually feels a smaller power. The power goes down, and so the radiation pressure force on it goes down, and the mirror pulls back in. So it's a restoring force. And that's really the principle of the optical spring. Okay? So it's a restoring force that comes from being detuned on this side of the cavity. Now, this is really just put up as for visual effect to just show you that these are sort of the standard things we assume in this experiment. It's given in a paper, so you can look it up. But basically, we make all these assumptions for the experimental parameters and imperfections. This is the key thing: is we also include imperfections like imbalance in the reflectivity of our beam splitter and so on to see how well could we do. We assume intensity noise at a few hundred hertz of 10 to the minus 8 per root hertz, relative intensity noise, and frequency noise of about 10 to the minus 4 hertz per root hertz. And people who think about this in terms of LIGO interferometers will know that these are hard but not extreme numbers at all. And this is then what you could do with an experiment should you build it. And I'll tell you in a moment what we are doing. So here are the noise sources that we considered. Now here we have frequency as usual, and on this scale I put the same scaling that people in the quantum optics community do, which is you normalize to the shot noise. So 1 over here is the shot noise or the quantum noise limit, and what you find is that we expect, this is our total noise as this orangish curve here, and we expect that we can do this well below the shot noise limit. And that limit, so you can say, okay, what's the limiting thing? So here, what's this funny resonance looking thing? This is the optical spring resonance, and that's the thing we move out to 5 kilohertz with the optical rigidity. And the noise budget then is really dominated by the green curve in this region here, and the green curve is really losses. So this is the intrinsic losses in our interferometer are going to limit us. But even with that, we've made reasonably realistic estimates for losses on mirrors and so on, and we think we should be able to see something. And seismic noise, for people who care, would really is in terms of this, if you make an equivalent displacement noise, would really not play a role in this region here. Okay, so that's what we're aiming for. The experiment at this stage is being done in 3 phases. The first phase is completed. It was a linear cavity, and in that cavity, now why do it in 3 phases? It's all to do with risk management. There are many things that are hard about this experiment. Probably the single hardest thing is the mechanical oscillator itself. Okay, so there are issues with power handling, because part of what we do is to keep the coding thermal noise small on the, I mean, our mirror is small, so first of all, our power densities are pretty large for the beam, but we also try to keep the beam as big as possible, and so there are risks associated with damage thresholds, but also with diffraction losses and so on. So we built this up in 3 stages. The first stage was a cavity we know how to build, and we actually had all the parts to build, so we built it. And what it was 2 quarter-kilogram test masses, mirrors, and it was a finesse of about 1,000, and we could put 4 watts of power into it. And in this phase of the experiment, we wanted to establish an optical spring, and something I haven't talked about at all, but I will in a moment, is to stabilize it. The next phase, which is what we're doing now, we replace one of those 2 mirrors with a 1-gram suspended mirror. We bump up the finesse to a few thousand, and we put in roughly, actually, I correct myself on the 1 watt, we're now actually putting in 5 watts into it, and I'll show you data from that now. And then the goal is to then, in the 3rd phase, make a second one of these, so make 2 identical cavities and then do the true differential measurement. And the ultimate goal, of course, is to get the quantum radiation pressure for the squeezing. So here is what the experiment looks like. I won't bore you with the details. Really, most people who've ever seen a suspended cavity know how the locking is done. It's a standard PDH with 2 paths, one feeding back to the length of the cavity, and then at high frequencies we also feed back to the laser itself. And that has a little bit of importance, because it means we have to know what our control system is doing, and that's the next thing. So if you ask now how to model this whole system, okay, so we have these mirrors, mirror oscillator, and we also have forces on it from the optical restoring force, and we have our control system, our electronic forces. So you start off with your mechanical oscillator, and it has your standard force per displacement given by this spring constant, which I call K mechanical. And onto that you add this optical rigidity, which I'll tell you about in a moment. The optical spring constant depends on the power in the cavity, the detuning, and so on. And the third thing that you add on there is your so-called electronic spring constant, if you will. It's just the forces you apply from your feedback system. And then you can model those all together as a composite displacement per force. Now, in the real world, it ends up being a Simulink model, since we're just not smart enough to do it in our heads. But once you get it all right, then you can, well, we are smart enough to write a few equations. So let me just tell you about these equations. There's 1 or 2 things that are important. You don't need to know everything about them. This is the optical spring constant. It's a function of frequency, so it depends on which frequency you go, but there are a few key features. Delta in here is the detuning of the cavity, gamma is its line width. So it just says what fraction of a line width of the cavity you detune will give you how much restoring force you get. But there's a key feature in the spring constant. It has an imaginary component. And this imaginary component is due to the fact that the cavity doesn't respond instantaneously to motion of the mirror. And in fact, what it ends up being is it ends up being a force term that's proportional to the velocity of the mirror as opposed to the position of the mirror. And this is the thing that makes the optical spring resonance unstable. And it's also the thing for people who think about parametric instabilities in interferometers, and I won't want to say enough more about it than to the experts. It's the exact same mechanism. It's it's this term here. And whether it's an important term or not simply depends on, so you can ask, where does this come from? It actually is basically the same thing as if you will, an optical viscosity. So whether this thing is unstable or not is just a competition between the optical damping, that term, or the mechanical damping. And something that's very pretty about our experiments is that since we work with these very high mechanical Q oscillators, we actually can really start seeing this competition between the light. The viscosity is a very low loss field, but we really start seeing this competition, and most systems can. So we have a very rich set of dynamics that I'll be ready to talk about in about 4 months with new data. In the meantime, there are a couple of things that you should notice. One is that the equation of motion is modified from an ordinary oscillator by this optical rigidity term. But more importantly, you also see this noise suppression. And the way to see that is that the force per displacement, so the response of your mirror to external forces, is suppressed by this factor of your measurement frequency over your optical rigidity as compared to when you don't have an optical rigidity. So does this really work? And this is data from the phase 1 cavity, so 2 quarter-kilogram mirrors. And we have a few things that are interesting about that. The one is the black points are data. The red is the fitted curve. And you notice 2 interesting things. First is that an ordinary oscillator would have the phase go from 0 to 180. And in this case, it actually goes from 0 to minus 180. In this case, it increases in phase. And this is evidence of the instability. And you can also ask, when you move this 1 hertz oscillator to 80 hertz, this is what we've done in this case, this corresponds to a spring constant of about 3 times 10 to the 4 newtons per meter. Now, if you want to put a scale on that, if you take the optical beam, the actual laser mode inside the cavity, and if you made an oak beam made of the same dimensions, you would get that rigidity. Yeah, except, of course, oak would give you a lot of noise. Okay, so the phase 2 cavity was the next thing we did. And the main goal for this stage, and this is the thing I want to concentrate on, is to see the noise reduction effects. Remember, in this case here, this dashed line is what the oscillator would look like without the optical spring. And we just didn't have enough room in here to make a compelling measurement of that. And the thing that we now have, so what does the phase 2 cavity actually look like? The only major difference, and that's cool and interesting for people thinking about how to make these mirrors, is here is our small little 12 millimeter diameter 1 gram mirror. It's attached to 2 glass fibers, and in this case there are small little glue joints at these 2 ends, and then it's attached to a ring glued at these points here, and then the rest of this system looks like the quarter-kilogram mirror. So we just stick this whole thing into a normal quarter-kilogram suspension. So here, this would normally be a quarter-kilogram mirror, like there is in the 40-meter or a mode cleaner mirror of LIGO, but instead we have in here this mirror. So it's a double suspension. We get some isolation from the 1 hertz system here, and then this fiber pair will give you a 30 hertz suspension. In our case, we have a little, I shouldn't say 30 hertz. So in our case, it's a 170 hertz oscillator. So this isn't the final thing yet. The final thing will really put this at about 10 hertz. Okay, and I can say more about how, but I won't.
That's before you put the optical spring on.
This is the mechanical system alone. Exactly. And then here is the noise suppression data from that system. And this is now a plot you're used to seeing. I'm sorry, I have a little bit of cutoff. This is frequency on this axis here. So here we are, 10 kilohertz down to 100 hertz. The green curve is, again, what you'd have without any optical spring. Now, how do you make this optical spring? Well, you lock the cavity with very low power. In our case, get, couple of hundred microwatts. Then you turn up the power, and then you start detuning it from resonance. This is how you march down to these curves here. And what you see, and I should point out that you have the dotted curves are data, but there's a fit from that Simulink model that's the solid curve, and you can't really see the differences except right over here at 350 hertz we have a spurious mode. It's the pitch mode of that little object that we don't control, and it's not in our model, so we don't model. But other than that, what you see is it's optical spring that starts at 170 hertz, and you can see a little bit of dirt in our data from that. and you start marching it out in frequency by the detuning, and notice a very key feature. Notice that this is really displacement per force. This is saying for the same external force that pushes this mirror, the mirror is moving by a factor of 10,000 less than it did without the optical spring. That's the suppression factor in there. Okay, so that's the way to look at that. Now, and that's really the key feature we were after, and is very important for our ultimate squeezing experiment. So the one last thing I can say about this is if you go all the way out to the 5 kilohertz, notice that the Q of the resonance also goes down. And that's that optical viscosity becoming more and more important as you detune further and further from the cavity resonance. So you're collecting more phase, if you will. So how to think about this 5 kilohertz optical rigidity? It corresponds to a spring constant of 2 times 10 to the 6 newtons per meter. And in fact, the optical cavity mode could be made of a diamond rod at that point. So that's the
No thermal noise.
what's that? Yeah.
What's going on at 1400 hertz?
At 1400 hertz. Yes, so that is another spurious mode. We have mechanical modes. And one thing we don't know about with this shell that it's mounted on, we think it's a mode of that, but we're not sure. But those are, anywhere where you see those things, those are spurious modes that shouldn't show up in the measurement. Okay, so I'll finish off by just telling you why one should work with this further. So what we've noticed is that we are studying the modified dynamics of these mirror oscillators. Now imagine that you were actually able to take this kind of, so these are systems in which your optical coupling completely dominates the mechanical system. So now if you could turn this into a quantum field, then you can actually really, the quantum state of the light actually is the thing that now affects the position of the mirror and not the external dynamics or external forces anymore. So it's a very key way of getting to regions of what we would call macroscopic quantum measurement, really where you can start thinking about creating the mirror in a quantum state, because you know now how to make up a very clean potential, if you will. And these are precursors to that. And the other thing, of course, that we want to look at is the role of feedback control in these quantum systems. And so far, we've seen nothing that isn't classical, to be completely fair. The spin-offs from this stuff are really just that we've developed a fully quantum code that's is used for advanced LIGO modeling as well. We did observe a parametric instability, which is given by the same mechanism, and so it showed up in the phase 1 cavity, and in our phase 2 cavity we had to do a few changes to get rid of it, but we also stabilized it by feeding back to the laser frequency. We can make diamond rods. And then finally, this mini mirror suspension actually uses a lot of the advanced LIGO suspension innovations in terms of microcircuits and so on. So, and tests of stabilizing the optical spring resonance out of band are very useful for advanced LIGO, because there is an optical spring, but that may also have to be stabilized outside of the band. So here is the reading list for tonight. And I'll end simply by telling you that advanced LIGO is supposed to be quantum noise limited, we think. And we do need these techniques to do better. And I think squeezing is probably one of the most promising, the most experimentally mature, especially when it comes to crystal squeezing. Upon remote squeezing, we're getting closer. I don't think that'll be the first squeezer to go on an interferometer by many years. But I think what it will be is it will become a test bed for macroscopic quantum measurement. You can see factors of 2 to 5 improvements in the future, because we don't see any fundamental limits. And we really need to start pushing on these things to be ready for future instruments. That's it.
In the long run, would you expect that ponderomotive squeezing will give you larger amounts of squeezing than crystal squeezing? You have the noise in the crystals, and the ponderomotive process is much less noisy.
Yes, so I would say eventually Yes, I mean, the difference between the two systems really is in these nonlinear crystals, there are the optical losses. Even though people have made big improvements, it's not clear where the next big improvement is going to come from. And in the case of systems like these, we're already using mirrors close to as good as you can make it. So I don't know which will go, further faster. But I would say it will be a good decade before a ponderomotive squeezer will become the workhorse of sub-shot noise interferometer measurements. I think we're at the point of starting to see the way. But
you use the term good vacuum. What's that?
Oh, it just means vacuum, as opposed to photons that contaminate the vacuum. So the idea is that if you have any light in that mode and it gets into your squeezer, it's going to come with its own noise. So good vacuum just means unadulterated vacuum. Jay?
Are the fundamental limits to how well you can do for the two approaches different? Not technical limits.
Yes. So you can ask what the, I shouldn't say fundamental, because really you can say what are the two limits, where do the limits come from? In the case of crystal squeezers, even though we don't achieve higher squeezing than that, Go has shown that if you consider most noise sources, take thermorefractive noise, and the basic things that are noise-producing mechanisms in these nonlinear systems, they're far below what will limit us, out at 10 hertz. So, is that fun? I mean, yes, is that fundamental? I don't know, but yeah, I would say the sky's the limit once you can get over the problem of the losses. So maybe I would still call that the fundamental thing. Cool.
So the ponderomotive effect is caused by the radiation pressure force pushing the mirror surface around the cavity in an intensity-dependent way. And there are other effects that also have a similar consequence, like photothermal effects or electrostriction. Do those play any sort of a role in the ponderomotive squeezing? Either as a trash effect or something you have to account for?
I don't know. We'll find out. We have not modeled those things. So I mean, the things we've modeled are on that curve, but one other curve which I didn't show because it would take too much work to explain, which is that the control noise is actually a big issue for us also. So stabilizing that 5 kilohertz resonance without getting any other control feedback in band has been hard. But I haven't looked at those noise sources. If you want to tell me they're bad news, I'm not listening. No.
So if control noise is a real problem here, how is control noise going to be in advanced LIGO on the optical spring?
There's two things there. One thing is, in advanced LIGO, over here, if you want to expose in advanced LIGO, just as an initial LIGO, you can have a feedback system on the mirror, and as long as you know what that feedback force is, it's a measure of your displacement. So, and in our case, what we don't have the luxury of is we really need that mirror to respond to the radiation pressure, and that's the difference. So we have a much more stringent cutoff on the control. That's the main thing I would say. And in advanced LIGO, I mean, maybe Ron can correct me. There isn't necessarily an intention right now to stabilize the optical resonance out of band. I mean, if you have to have a 40 hertz or 100 hertz, 40 hertz bandwidth, you might. It's always in band. So that's right. In our case, we couldn't do that because the optical spring is well outside our band if we want to measure the squeezing there. All right.
Let's thank you.